Welcome to Chapter 5 of the Front-End Planning series, Cost Planning, Budget Validation, and Funding Strategy. In this chapter, we will look at how early cost planning evolves from a rough estimate into a reliable budget that can support major capital decisions. In the early phases of a project, the team usually does not have complete drawings, detailed quantities, final specifications, or firm vendor pricing. But even with incomplete information, the owner still has to make important decisions. Is the project financially reasonable? Which alternative should move forward? And how much funding should be released for the next planning step? The key message of this chapter is simple. Funding decisions should follow the maturity of the scope. They should not be driven by optimism, pressure to proceed, or a number that looks precise but is not yet supported by project definition. Cost planning and detailed estimating are related, but they are not the same activity. During front-end planning, the project team is usually working with limited design information. At this stage, estimators often use top-down or stochastic methods. These may include parametric models, historical benchmarks, cost-to-capacity ratios, square foot costs, or comparisons with similar projects. The purpose is not to price every detail. The purpose is to test feasibility, compare alternatives, support the business case, and help the owner make early go or no-go decisions. As the scope becomes more mature, the estimate can shift toward a bottom-up or deterministic approach. That is when quantity takeoffs, vendor quotes, labor productivity assumptions, subcontractor input, and detailed unit costs become more useful. One of the most common mistakes in capital planning is asking for a narrow, highly precise number too early. When the scope is still immature, a single-point estimate can create false confidence. It may make the project look more certain than it really is, and it can lead the organization to commit to a budget the project cannot realistically meet. Good front-end planning does not hide uncertainty. It explains the uncertainty, shows the expected range, and identifies what additional information is needed to improve cost confidence. Estimate classification helps the project team communicate how reliable an estimate actually is. The AACE Estimate Classification Framework connects estimate class to the level of project definition. A Class 5 estimate may be based on only 0 to 2% project definition. It is useful for concept screening and early business case discussions, but it has the widest uncertainty range. A Class 4 estimate may support feasibility studies and comparison of alternatives. It is more developed than a Class 5 estimate, but it is still not appropriate for final authorization. A Class 3 estimate is typically used for budget authorization or final investment decision. At this point, the project should have stronger scope definition, more reliable assumptions, and a more developed basis of estimate. Class 2 and Class 1 estimates are used later when the project has much more detailed definition. These estimates support procurement, bid comparison, execution control, and detailed validation. The important point is that the estimate class must match the decision being made. If a low maturity estimate is used for a high commitment decision, the unresolved uncertainty does not disappear. It moves into execution, where it often appears as change orders, claims, contingency depletion, and loss of confidence in the project team. A reliable project budget must separate different types of cost provisions. Contingency, escalation, and allowances are sometimes used loosely, but they serve very different purposes. Contingency is for expected uncertainty within the approved scope. It covers known unknowns, such as normal design development, minor estimating omissions, productivity variation, or identified risks that cannot yet be priced exactly. Contingency should be connected to the project risk register, and it should be reduced only when specific risks have been retired, transferred, or mitigated. Escalation accounts for expected changes in labor rates, material prices, equipment costs, and market conditions over time. If a project will purchase major equipment or materials months or years after the estimate is prepared, escalation needs to be modeled against the procurement timeline. Allowances are different. They are specific budget amounts for known scope items whose final details have not yet been selected or designed. For example, a project may carry an allowance for specialty lighting, laboratory casework, seating, landscaping, or owner-selected finishes. The key lesson is that these items should not be hidden inside one general reserve. Each provision should be visible, documented, and used for the right purpose. Contingency should never be reduced simply to make the budget look more acceptable. A cost estimate is only as reliable as the assumptions behind it. That is why the Basis of Estimate, or BOE, is one of the most important cost documents in front-end planning. The BOE explains what is included, what is excluded, what estimate class is being presented, what quantity basis was used, what pricing sources were applied, and what labor productivity assumptions support the estimate. It should also explain how contingency and escalation were developed. Budget validation is the process of testing whether the estimate is appropriate for the decision being requested. For example, does the estimate class match the funding decision? Are site work, utilities, permitting requirements, and owner requirements included? Are long lead items supported by current vendor input? Does escalation follow the procurement schedule? Is contingency tied to documented project risks? The BOE should also remain connected to the basis of design. If the basis of design changes, the BOE must change as well. If an excluded item becomes part of the scope, the cost impact should be documented. If a risk is retired, contingency may be adjusted. For major capital authorization, budget validation should include an independent review. This gives decision-makers confidence that the budget is not just a number, but a disciplined financial baseline supported by scope, assumptions, pricing logic, and risk analysis. Cost planning during front-end planning should not focus only on the lowest initial construction cost. Owners do not simply buy a facility, they operate it, maintain it, repair it, and eventually replace or decommission major systems. For many facilities, operating and maintenance costs over the life of the asset can exceed the initial capital cost. A project that appears inexpensive to build may become expensive to own. This is where life cycle cost thinking becomes important. For HVAC systems, the team should compare energy use, maintenance complexity, controls capability, replacement cycles, and occupant comfort, not just the initial equipment cost. For the building envelope, the team should evaluate thermal performance, moisture durability, maintenance requirements, and long-term energy savings. For electrical infrastructure, avoiding spare capacity may reduce first cost, but it may also limit future expansion, reduce resilience, and increase the risk of costly downtime. This also changes how we think about value engineering. True value engineering is not simply cutting scope to reduce first cost. It is a structured effort to improve the relationship between function, performance, and cost. Sometimes the best value is not the cheapest option. It is the option that delivers better long-term performance for the owner. Cost planning is not only about producing a budget, it is also about supporting a responsible funding strategy. Major capital should not be released simply because the project sounds exciting or because an early estimate appears affordable. Funding should be released in stages based on scope definition, cost confidence, risk maturity, and strategic alignment. In concept planning, limited funds may be released to define the mission need, screen alternatives, and test early feasibility. As the project moves forward, additional funding may support site investigations, preliminary design, vendor engagement, constructability review, and risk analysis. Full construction funding should come only when the project has an investment-grade scope, a validated estimate, a realistic schedule, and an approved execution strategy. A stage-gated approach protects the owner from committing too much money too early. It also creates a disciplined relationship between planning quality and funding authority. If the project is not ready, a recycle or conditional go decision should not be viewed as failure. It may be the most financially responsible decision because it gives the team time to resolve uncertainty before that uncertainty becomes more expensive during execution. Before a project reaches a major funding gate, the project team should test whether the cost baseline is truly ready. First, is the estimate class clearly stated, and does it match the decision being requested? A Class 4 estimate may support continued planning, but it should not normally support full construction authorization. Second, is the basis of estimate complete? The BOE should document inclusions, exclusions, assumptions, pricing sources, quantity basis, and contingency methodology. Third, are site conditions, utilities, permitting requirements, and escalation included? These items are often underestimated early, but they can have major cost impacts later. Fourth, is contingency tied to project-specific risks rather than an arbitrary percentage? A flat percentage may look simple, but it may not reflect the actual risk profile of the project. Finally, does the funding request match the current maturity level and the owner's business case? The goal is not just to approve the project. The goal is to approve the right amount of capital at the right time, based on the right level of information. Let's apply these ideas to a university science and health professions building. During FEL1, the university developed a Class 5 benchmark estimate of approximately $95 million. This early estimate was useful for concept screening and business case development. The need was clear: outdated instructional laboratories, growing enrollment in health-related programs, and a desire for more flexible teaching and research space. During FEL2, the team compared renovation, a smaller addition, and a new building. At first, renovation appeared less expensive. During FEL2, the team compared renovation, a smaller addition, and a new building. At first, renovation appeared less expensive. As the preferred new building option moved into FEL3, the project team developed a more mature Class 3 estimate. Specialized lab ventilation, simulation suites, emergency power, utility extensions, and electrical service upgrades became more visible. The estimate increased from $95 million to $112 million. At first, leadership was concerned, but the FEP team used the basis of estimate to explain that this was not simply a cost overrun. The new number reflected better scope definition, vendor pricing, escalation analysis, and risk-based contingency. Life cycle cost analysis also influenced the decision. A lower-cost HVAC option would have reduced first cost, but it would have increased energy use and maintenance complexity. A higher performance system cost more initially, but it provided better long-term value and more reliable laboratory operations. In the end, the board approved the $112 million budget because it was the better supported number. They also authorized early procurement of critical electrical equipment to protect the schedule. The lesson is clear: a higher but well-supported estimate is often safer than a lower estimate that hides uncertainty.